This is AP Precalculus. We're on topic 1.2, the rates of change. These are the notes that we left off with from the video from yesterday. And you'll remember that we were doing a Texas Instrument TI-84CE calculator, which took a lot of work to do these. I don't think we finished part D in class, but I want to show you how you would do that on a Desmos calculator. I would prefer if you guys didn't touch the TI-84CEs while I'm not there, because I haven't distributed them officially yet. I want to show you how easy this problem is to do if I had done it all in a different calculator. So let me go ahead and do a split screen with my scientific calculator. So what I'm going to do is I'm going to make a new function. I'll call it h of x instead of h of t. So all the t's will switch to x's. I'm just going to type in this equation almost exactly. So I see h of x, and that's going to be equal to, I need to go outside the parentheses. It's going to be equal to, and then I have some numbers. So it's going to be negative 4.9, and it's going to be x squared. So x squared, and plus 25x plus 25x, and then plus 5. And just to test that this is working, let's try to say h of, I don't know, 1. And it seems to be working. So it says it's 25.1. What I want to do is I want to enter this exact equation to see if I get 14.71, just to check that our calculator is working. So the way that I do that is it's going to be actually 1.1 here. It's going to be a fraction. So on the top of the fraction, we're going to have minus h of 1. Minus h of 1, and then on the bottom we're going to have 1.1 minus 1, and it's 14.71. So it seems to be working. What I'm going to do now is enter this equation. So over here I'm going to say h of 1 minus h of, not 1, but 0.999, and on the bottom I'm going to, let's go ahead and get rid of everything. It's going to be 1 minus 0.999, and we get about 15.2049. So let me make this have some more room. I'm going to say, can I zoom in here? That'll be better, won't it? That will be equal to 15.2049. And done with the calculator for now. And then it's asking this question, based on example 4, based on all of these inputs, what do you think the true rate of change? Again, the true slope. Whenever I see the words rate of change, I kind of, in my head, cross that off and say slope. What do you think the true slope when I'm at t is equal to 1? And what do you think it is? I mean, it looks like I'm getting 14.71, 15.15, 15.19, 15.2. I don't know. It seems to be around 15-ish. And this is, I would say that it got more and more correct because we went from 0.1 to 0.01 to 0.001. This one is probably really, really close. And if I go from the other side, it's 15.20. So what do you think it is? I'm going to kind of average this number and this number. I think the average there is about 15.2. So that's my guess. You might have a different guess than me. That's fine. I would say that the rate of change, I'm going to say ROC, is probably 15.2. Just because that's in between that range. What? I don't know. I brought it downstairs somewhere. I thought I did. Okay. So it's telling us now that the rate of change is of a function at a particular point is the rate at that the y values would change if the x values changed at that point. Okay, that doesn't really tell me anything new. This concept is what we would call instantaneous rate of change. And we'll do that later in AP Calculus. So when I have a slope just at 1 point as opposed to 2 points and I just make a line, you can't have a line that goes through 1 point. It's called a tangent line. But again, usually we talk about that in AP Calculus. So let's keep reading. While we cannot find the rate of change at a particular point in AP Precalculus, that's reserved for AP Calculus, we can do the following two things. We can blank the rate of change at a point by finding the average rate of change over a very small interval. I don't have an answer key in front of me, but I'm going to go ahead and say this is probably estimate or approximate. the rate of change. And 2, we can blank rates of change at 2 different points by estimating individual rates of change using the concept of a tangent line. But I feel like the same word is going to be down here. We can estimate rates of change at 2 different points by estimating individual rates of change using the concept of a tangent line. I really wish I had an answer key in front of me, but I guess calculate might also make sense in this blank. We can blank rates of change at 2 different points by estimating individual rates of change using the concept of a tangent line. I don't know, guys. I'm just going to say estimate again. I think the main message is when on one hand we can do very small interval, and on the other hand you can use a tangent line. They're basically the same thing if you get small enough intervals. Note, we discussed the rate of change, I'm just reading down here, of a function. We are essentially discussing the slope of the graph. And I've said that over and over again. Slope is the way that I'm characterizing every time we say rate of change. It's really just slope. So it's now finally using the word slope like I do. In the graph of f, or if the graph of f has a positive rate of change, that means it's a positive slope. And the graph of f is increasing, because increasing means that we're going up, which means we have a positive slope. Likewise, if the graph of f has a negative rate of change, it's going down, it's decreasing. Okay, all of that makes sense, but it's nice to have it written down for us. All right, example 5. For each scenario below, determine whether the 2 quantities typically have a positive rate of change or a negative rate of change. There are other words that we sometimes hear in math. So I think, I'm trying to remember what they're called, but like you have a positive relationship or a negative relationship or something like that. But positive means with one goes up, the other one also goes up. So that's positive. Let's read. A child's age versus the child's height. I mean, generally speaking, if you're talking about the child is always growing. So as the child goes up in terms of age, does its height also go up? Yes, so this one is going to be positive. Okay, a golfer's skill level goes up, and then the golfer's score, okay, well, in golf, you want a low score. You want to take as few swings as possible to get the ball in the hole. So hopefully they have a lower score because they're better at the game. So this is a case where it's backwards, right? This skill level goes up, but the golf score goes down. That's a good thing, but that's a negative association. Sometimes people call that an inverse relationship instead of a direct relationship. And then C, what do we have here? The height from the ground of a coin dropped off the Burj Khalifa, I don't know if I'm pronouncing that right, versus the speed of the coin. All right, so the height, it's going to be some really big number, and then it's going to get smaller and smaller and smaller and smaller. So hopefully, if it's a positive rate of change, then this one will also get smaller and smaller and smaller and smaller. The height gets smaller and smaller and smaller because it's going down towards the ground. And eventually, it's going to hit the ground where the height is 0. But the speed will go up. It'll go faster and faster and faster. So this one is also negative. Because one thing goes down and the other thing goes up. Height goes down, speed goes up. So if they're opposite of each other, then it's negative. All right. We're on to estimating rates of change at a point. So we're trying to find these. These are called tangent lines. Because they touch at just one point, as opposed to touching at 2 points. If I had a line going through 2 points, that would be called a secant line. So I'm going to write down secant just in case you want to know it. Or maybe it's going to say it down here. Maybe I should read this first. I might be getting ahead of myself. I haven't looked ahead of this. So the graph of f is shown above the line, along with the line. There's the word I'm looking for, tangent. Tangent to f when x is equal to 4. In calculus, we will learn that the slope of the line tangent to the graph of f at any given point is a true rate of change. And when I say true, it is the actual rate of change. We don't have to approximate using a secant line. And I don't think they said secant line in here. So when we have 2 points and we make a line through that, that's called a secant line. And again, we can't do the tangent line until we have calculus. Yes, we already know this. While we cannot find this slope in AP Precalculus exactly, we can sketch the tangent line and estimate the rate of change. So in example 6, we want to estimate the rate of change of f when x is equal to -4. Okay, so I think it's already been done for us, but when I'm at -4, when I'm at this spot on the graph, and it looks like there's the slope of the tangent line. So there's the line, but again, we're looking for the rate of change, which means we're looking for the slope. So what's the slope of this line, more or less? It doesn't go through any lattice points. It doesn't go through any like crosshairs here, 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 here. I mean, it's kind of close to that lattice point. It seems to be going up a little bit more than 1. I'm going to call it maybe 1.2. I'm not sure, but it's a little bit steeper than 1, so I'm going to go ahead and call it about 1.2. I don't know if there's a more exact way to do it. I guess here, what's another way of doing it? I'm going to go ahead and pretend that that's a lattice point. What do we get? So I'm going to go up 1, 2, 3, 4, 1, 2, 3. So I went up 4, right 3. So I'm going to say it's really close to 4/3, which is actually 1.3, not 1.2. So my original estimate was a little bit off. It's about 4/3. Example 7, sketch the tangent lines to F at 5 points indicating the graph above. Okay, we can do that. So you should try to do this ahead of me. I don't want you just copying down what I'm doing. But essentially in my mind's eye, I'm thinking of like a point here and a point here, and I'm connecting the 2 points, and that is essentially the tangent line. So my tangent line is going to go right there, and I have another tangent line right there, and I have a tangent line that is horizontal at this point, right? Should be nice and flat. Ooh, I'm having trouble making a horizontal line. And then I have a tangent line. Ooh, that's a little bit off. A tangent line like that, and then a tangent line like that. The problem with functions, when you zoom in really, really close, it looks like the line is on top of the other line, especially when we make the lines thick like this. If it was a very thin line, you could see that the tangent line goes off. If I zoomed in forever and ever and had infinite accuracy, you could see that there were definitely different lines. But unfortunately on this graph, it looks like I'm just on top of the line. These are all supposed to be straight lines. They're not supposed to be curved lines. Tangent lines and secant lines are lines. They're not curves. All right. I did example 7. Example 8. Does the graph of f appear to have a greater rate of change? So again, every time I see the words rate of change, I'm just going to cross you off and change that to slope. So now the question says, does the graph of f appear to have a greater slope at x equals 4 or x equals 5? And we need to explain. And this is just something to get in the habit of. Every time we're in AP and it says to explain, if you don't explain, you lose a point. Or many points, depending on how complex the explanation is. So at x equals 4, x equals 5, let's go ahead and take a peek. And so x equals 4 is this slope right here, and x equals 5 is this slope right here. I would say that this slope is slightly steeper than this slope. And you can just eyeball it, but there is a more interesting explanation. It's the fact that this is concave up. When we're concave up, points farther to the right, I guess, or farther away from wherever we had the turnaround spot will be a steeper slope. So here's the vertex. This line is not as steep as this line, and you can say this line is not as steep as this line. The farther we move away from the vertex, the steeper the line gets. So I'm going to say steeper at x is equal to 5, and now we need to explain. I'm just going to say because concave up and 5 is farther away from the vertex. Where is the vertex roughly? It was kind of right here at x equals 2-ish, right? I'll just say x equals 2. X is about equal to 2. Then x equals 4. Nice. All right. I think that's the... Oh, wow, we have 2 more pages of notes, and then it moves into the worksheet, which you guys are going to be doing on your own. I don't have enough time to record that video. 2 more things. Let's keep reading here. Rates of change in the graphical behavior. So we're going to connect rates of change of f with the graph of f. So if the rate of change is positive, then the graph is increasing. Okay, if the rate of change is negative, then the graph is decreasing. I mean, all of that sounds pretty straightforward. If the rate of change is increasing, then the graph of f is concave up. So we're changing from the word positive to increasing. If this thing right here is increasing, if this rate of change is increasing, then we're concave up. We could still be negative and increasing. You can mix this word with this word, and you can mix this word with this word, right? You can be increasing and concave down, or you could be increasing and concave up. It's up to you, but it's talking about if the rate of change is increasing, that will determine if you're concave up. This is kind of a cool little chart of showing you how to use words to describe concave up. Rate of change increasing always means concave up. This is probably something that I should add to a speed sheet. I'm thinking out loud as a teacher. All right, so let's read example 9. The graph of f is shown above. Complete the blanks below to correctly describe the graph of f and the rate of change of f. So rate of change, again, I'm just going to cross you off and say slope. All right, so on the graph of f, I mean, it looks like f has been cut off a little bit. This should say f right here. The graph of f is, well, wouldn't you agree that the slope here is positive? So that means increasing or decreasing is talking about the slope. The slope here is positive, so it's increasing. And what is it doing? Well, it's going up, but it's concave down. It's constantly being pulled down, being pulled down, being pulled down more and more and more. This is being concave down. Again, concave down is kind of like a rainbow. And that's because the rate of change of f, again, every time I see rate of change, I'm kind of thinking of crossing it off and saying slope. Because the slope of f is, well, what is the slope? The slope is going up, so the slope is positive. So positive. And the rate of change of f is, again, so cross off rate of change and say slope. What is the slope doing? Is the slope getting steeper and steeper and steeper, or is it getting less and less steep? Well, it's getting less and less steep because it's super steep right here and not as steep right there. Therefore, the slope is decreasing. So it's going to be decreasing. We can say decreasing. Okay. This is a great way of explaining if you're increasing and concave down. How do you explain that? And it's because the rate of change is positive and the rate of change is decreasing. It's using all this academic vocabulary. I'm hoping that you guys will be able to start saying this in free response questions. AP tips and insights. Okay, be careful when answering questions about graphical behavior! Exclamation point. Pay close attention to the wording of each statement. Does it refer to the graph of f or the rate of change of f? Oh, that's tricky. Yeah, so that's nice to know. Are we talking about just the heights, or are we talking about the slopes? That's essentially what it's saying. So I'm gonna write down my own interpretation of that. Is it referring to heights of f, or are we talking about slopes of f? Because those are very different things. All right, so when I say the graph of f, in example 10, I immediately am saying the height. And when I see rate of change, I change that out to a slope. And then if I see graph of f, again, I'm switching that to the word height. And when I see rate of change, I'm changing that to slope. Okay, so I should probably read the instructions. Example 10, for each of the following graphs, circle the correct descriptions of the behavior of each graph. Okay, we just have to circle. It's going to go faster. That's why this was such a long lesson. All right, well, what do you guys think about the heights? Are the heights positive or negative? Are the heights above the x-axis, or are they below the x-axis? Well, it's clearly above, so the heights are positive. You can say the graph of f is positive. Okay, what about the heights? Are the heights going up, or are they going down? Well, heights appear to be going down. This was a nice high height, then lower height, then a lower height, then a lower height. So the height is decreasing. So you can say the graph of f is decreasing. Okay, but now let's talk about the rate of change. The slope of f is, well, all of f, this slope, this slope, this slope, all of these slopes are negative. Circle negative. And what about the slope? Is the slope going up, or is it going down? So I have a very, very downward slope, and it's not so down, and it's almost zero. It's constantly being pulled up, being pulled up, being pulled up. So it's actually increasing in terms of the slope. All right, again, in each of these, you're switching out in your mind's eye that the graph of G is really just talking about height. This is talking about height. And whenever you see rate of change, switch it out for slope. Switch out rate of change for slope, and then answer the question. So in this graph, what are the heights? The heights are always negative. All right, so we're going to circle negative. And the heights are going up or down? Well, the heights are progressively going up and up and up. So the heights here are increasing. All right, what about the slope? The slope is positive, 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 positive. Those are all positive slopes. And finally, is the slope going up or down? Well, check it out. We had a really, really big slope. Remember, if I have a slope that's straight up and down, that's infinity for the slope. So the slope is slowly going down and down, and slope is eventually going to 0, so it's decreasing. Yeah, that's looking pretty good so far. Let's go ahead and do another one, and then we have the back. Oh, and then it's the worksheet. Okay, cool. Almost done. So again, it's annoying and it's tedious, but you have to switch out. Graph of h is just asking about height. And graph of h, you're really switching this out for the word height. Rate of change, switch it out for the word slope. Rate of change, switch that out for the word slope. And we ask the question, the height is what? Well, the height is always above the x-axis, so the height is always positive. The heights are going up or down. This height, this height, this height, this height, this height, they're clearly going down, so they're decreasing. What are the slopes? The slopes here, that's a negative slope, that's a negative slope, that's a negative slope, that's a negative slope. All those slopes are negative. And finally, is the slope going up or down? Well, check it out. I had a slope that was essentially, well, I'm gonna do this in laser pointer. I had a slope that was almost 0, and then it starts accelerating more and more. The slope is actually decreasing because it's going down and down, further and further and further. So I'm going to say decreasing on this one. The slope is decreasing. All right. You can say it's getting steeper, but it's steeper in the negative direction, so therefore it's decreasing. I'm like only 90% sure about that last one, because it feels like the slope is getting steeper, but it's not asking steeper, it's asking increasing. That means going up and up and up and up, or is it decreasing, going down and down and down and down? This is one of those cases that's going down and down and down, so therefore it's decreasing. All right, so that concludes the rest of our notes that we've started from yesterday. What I'm expecting you guys to do today is to work through all of worksheet A, and then hopefully, I'm just taking a peek here. Yeah, it's a bunch of those review questions from the notes. You have to do some stuff with graphs and tables. What else do you have on worksheet A? Yep, easy peasy stuff. It uses a bunch of table from an actual SAT question. There's those questions. And you guys have worksheet B that I pass out as well. I think you guys should be able to finish worksheet A and B in class. So let's see how far you guys can get, and I'll talk to you guys again on Friday. All right, bye.